Hi, I'm Haakon Fossen, professor at the University of Bergen, and I'm going to talk about faults and their relevance to petroleum geology. This presentation gives some glimpses into the world of faults and is meant to be an inspiration for further studies rather than a complete coverage of what is a very, very large topic. So here is the contents. We'll talk about what a fault actually is, how we can map and study faults, how faults form, displacement and growth, fault populations, and finally faults and fluid flow. So what is a fault? Well, a fault is characterized by shear displacement, which means displacement parallel to the fault itself. Whether we are in the extensional regime, the contractional regime, the strike-slip regime, it's always movement parallel to the structure, to the fault. The other thing that characterizes a fault is brittle deformation mechanisms, which means fracturing and frictional sliding at the micro scale. And this happens mostly in the upper part of the crust, as illustrated in the figure to the right, upper right. The upper 10 to 15 kilometers of the crust is where we primarily form faults. Deeper down we talk about shear zones, mononite zones forming in different ways by different deformation mechanisms. We also make a distinction between very small faults, I call these shear fractures, like the left side picture here, shear fracture, very small, very simple, very clean, different from the right side picture showing a small fault with a more complex and composite structure. There are different ways of describing and classifying a fault in terms of its internal structure, because there's a lot of variation. But one is the upper right here figure showing a fault zone with several parallel fault shear features and smaller scale features around in what's called the damage zone. And the lower left we have a more developed rock where we have a fault core that includes lenses of less deformed rock, and again the damage zone with smaller scale deformation features around this fault core. And in addition to this we also have drag as shown in the lower right here, normal and reverse drag that can be of importance. So how can we map and get information about faults? Well, there's field observations, seismic data and experiments. And field observations are really good for details, small scale geometry, fault properties, kinematics, and sometimes we find very nice examples to study. This is a nice, not so common example from southern Utah where you can study a fault zone reverse in this case, from different angles, different sections, and work out the 3D geometry for this, at this scale at least, and also go in and check details. In this case we have smearing of a fine-grained layer up along the fault. Then we have seismic data, which is an amazing tool, especially new high-quality data, 3D data, which you can use to map faults in all directions, their geometries, their variations in offset, and relate the deformation of the rocks around. Here's an example of a seismic cross-section that shows faults very nicely and the way they change dips from steep in the upper part and then shallowing and get some of them getting steeper again, so non-planar geometries. If we add some interpretation here, the light blue line in the middle and upper right is the top of the basement, the crystalline basement, so we can see how these faults extend and can be mapped deep down into the basement, into the crystalline crust, and also the way they affect sediments above. Now on a seismic section, a fault is usually just a line, but a fault is much more exciting than that. faults are actually tabular volumes that contain, as we have seen already, very interesting internal structures. And in this slide I'm trying to relate the seismic image to the right and the outcrop image to the left to show the difference in scale. I mean, the outcrop picture illustrates complexities that are way too small to be seen in the seismic section. So we need both scales of observations to understand faults. Then the other way we can learn about faults is by doing physical experiments. There are many ways of doing that. This is a sand with clay layers, imposing an offset and studying how the clay layers smear out to form a sealing fault in this simple experiment. Then we have numerical modeling that now allows us to make faults, to grow faults in, for example, this numerical sandbox, and see how faults develop and interact. Then we're going to talk a little bit about how faults form. And there is a classical way of illustrating that, the layer cake, or the clay cake model to the left here. Clay cake put on 2 pieces of wood, and we move the wood plates and the clay deforms, but it doesn't form a single straight fault. It forms a series of out of plane structures, small shear features that are oblique to the main orientation of the zone. And in this case, these are the R or Riedel structures developing. And in the upper figure, you can see a lot of other small scale structures that can form as a fault is about to nucleate, to initiate. The R prime, P shears and extension structures like tension gaseous and so on. And here's an example of how this may play out in nature. This is a surface breaking, ground breaking rupture from an earthquake in New Zealand. And we can see that the fault that is forming here consists of at least 2 different sets of structures. And these are R and R prime. Riedel shears in red here. And we remember the orientations like this. And the zone itself is defined by these black lines, so they are both oblique to the zone. But then they interact, they link up, and at some point we form a continuous fault, but a complex one. This is a small scale example in the middle and an experimental example in the bottom, where we can see the Riedel shears dipping to the right and connected in this case. And in the lower experiment we can see the fault is now a continuous feature, but with all kinds of small scale complications along strike. In other cases there may be extension features, veins forming, like this limestone shale situation that this illustration shows, where the strong limestone develops extension fractures, and these then link up through the shale, and we get a rather complicated fault with all kinds of changes in orientation. And then in porous sandstones we get what's called deformation bands, and faults form by the formation of single deformation bands that interact and form clusters of deformation bands, and then eventually a fault grows in that zone of deformation. This is what a deformation band fault could look like. This is from Brazil, the northeast. Lots of small scale deformation bands forming. And these are not fractures. They don't conduct fluids. They actually involve a reduction in porosity and permeability that we'll come back to. And if we look at this sandstone here, there's a deformation band white in the middle. And if we look at that under the microscope in thin section, we can see how the original grains are fractured, very small very small grains that are packed tightly together, reducing the porosity and therefore the permeability. Now, ideally, when a fault forms and grows, it takes on a characteristic displacement pattern, a pattern of displacement variation, which is, of course, in the tips, or the tip line. The displacement is 0, but increases as we get closer to the central part of the fault. That's illustrated by this graph in the upper figure, when the displacement, the maximum displacement is located in the middle. And in 3D, or actually 2D, the fault surface itself, if you wish, can be contoured with respect to displacement, and ideally, very idealized, it could look something like this: the Dmax, maximum displacement, in the middle of this fault surface. There is the same thing again, showing tip points in different sections. The figure to the right shows a natural fault that has been mapped on from seismic data and contoured from 0 to 50 meter offset, 50 meter more or less in the middle. Now, if you make a section through that displacement map, you get a graph like the one in the lower right here, displacement increasing towards the central part of the fault. And then you can calculate the gradient from the tip to the center, to the maximum. And this gradient is of interest. Here's about 0.06. Let's have a look at what that means. Now, there's an interesting relationship between length and displacement. Irrespective of the size of the fault, this ratio between the two is more or less constant, which is illustrated in this graph here. Length along the horizontal axis and the maximum displacement along the vertical axis. And you can see that there is a nice relationship between the two. So if you know one of them, you can calculate the other one, or get some idea at least about the other parameter. And it also tells you something about the gradient, how fast the displacement changes along a fault, which is, with some variation, quite a bit of variation, but it gives you an idea. The displacement can change if you move 1 kilometer along the fault by 10 meters, by 100 meters, or something in that range for most faults. When we map actual faults, we oftentimes see that the displacement is not so simple, it's more complicated. Like this example here, we have many fault displacement maxima, and also the fault itself is not a clean surface. It's a composite structure in some parts of the fault. And there's an explanation for this. And maybe we'll look at this simpler fault here. This is a fault in black in the upper map from A to C. B is sort of the middle part. And if we look at the lower diagram here, we can see two sort of reddish centers, which is displacement or throw maxima. And these maxima occur, so there's not one maximum on this fault, there are two maximas. And they occur in two places. Let's put that on, two maxima, and they occur at these two locations on the fault map. And the obvious interpretation here is that we had two fault segments basically growing together to form one much longer fault. And these two maxima are maintained for some time after such a linkage process has been completed. Now we can study linkage experimentally, just to give you an idea what we're talking about here. For example, this Plaster experiment shows in the upper left incipient faults, very small faults, drawn out in the right here on these maps, and we can see how as strain accumulates downwards, these faults, the small faults, connect, link up, and form a long continuous fault, but with many irregularities that relate to the history of this fault, the history of linkage. In the lowermost right corner we can see F3, F4 and F5, and these also will link up. Let's continue the experiment on the right, upper right here. These now link up to form another long fault that is not completely linked up from one side to the other in the experiment, but it will if deformation continues. In these linkage sides we have something called relay structures or relay ramps, where the layering is bent into a ramp. These are quite important structures too. Here is an example from the Canyonlands in southern Utah. We have actually two sets of faults here, but let's focus on the left set of faults. There's a fault running down this, actually a graben, and then there is a ramp, and another fault continues. Let's go down on the ground and have a look at that. Here is a ground view, one fault bleeding out to the right, fault 1, and then fault 2 picking up the displacement. And in between there is a rotated or folded part of the stratigraphy. And that's the ramp. It's starting to break up with these yellow dashed lines indicating small faults. And on the right we can see the general development of a ramp from its early beginning in the upper 2 and 3 figures, and then the two faults connect and the ramp is breached, cut off, with a lot of subseismic, usually small-scale deformation in that particular region. Then let's look at fault populations. Many faults together in a region that experienced some deformation. This is a Google Earth view from the East African Rift, where we can see from the shades here, the shadows from the cliffs, indications of faults, many subparallel faults, but with small irregularities that have to do with linkage processes. There's a volcano for scale here. Here on the left is a simple, very simple model of fault growth, fault population formation, and it starts out with lots of scattered small faults distributed randomly throughout our region of interest. And then as these faults propagate, the tips propagate, some of them will link up quite rapidly and define more continuous and longer faults that would take over the strain accumulation, and then the other small faults will remain inactive more or less. On the right is a figure that reminds us that there is also deeper structures in most cases, and in many cases at least, that get reactivated and influence exactly where and how the faults in the cover will develop. So both of these aspects have to be taken into consideration. Here are two maps of actual fault populations from a rift. The map to the left has experienced less strain, or reflects less strain. It has a lot of parallel small-scale faults and some larger faults that make bends that indicate that they form by linkage. On the right we have a more mature fault population, higher strain, and we can see a larger variety of orientations. And the red faults that are marked here are faults that formed relatively late, and we can see that the small late faults have different orientations to a large extent than the other faults and the main faults. Here's an example from a coal field where the faults have been mapped in great detail, and the map to the left shows large faults, displacements larger than 20 meters, and the map to the right shows the smaller scale faults, and we can see the differences in orientations. The small scale faults, for example, have a lot of northeast, southwest trending faults that don't show up so much in the large scale fault picture. So again, there can be a difference between the orientations of large and small faults that we need to take into consideration. Now let's focus more specifically on faults and fluid flow. So there are the large faults that are positive in this sense, since they can create structural traps, as shown on this picture here, with rotated fault blocks and an overlaying shale, for example, that can act as a cap rock. But then there are the smaller faults that are less predictable. They can affect reservoir performance during production. And it's important to realize that different kinds of structures can have different influence on fluid flow. For example, deformation bands here on the left will reduce permeability and negatively influence fluid flow, while fractures, as shown on the right, will conduct fluids, so it will have the complete opposite effect on fluid flow. There's an example of a fault that has a reddish color, and the reddish color is an indication of fluids depositing, probably hematite or iron oxide in the fault zone. So this is an example of a long fault fluid flow. Then there is cross-fault fluid flow that has to do with the communication within a reservoir. And we talk about sealing and non-sealing faults, and there are different kinds of seals. For example, we have the obvious one in the top of this figure, juxtaposition seal, where there's an impermeable rock on one side of the fault, so it's quite clear that there has to be sealing, the fault has to be sealing. Then there is self-juxtaposed seals, and that's where the reservoir is in contact with itself across the fault, so the seal has to be produced by the fault rock itself, something like this. And then we have shale smear seal, number 3, that involves the smearing of shale along the fault. So the latter two are the most important ones to look at more closely. There's a few pictures from crushed rocks, and that's what happens in some fault zones, is that minerals are crushed, grains are crushed, compacted, cemented maybe too, and we get less permeable fault rock. And the question then is that enough to seal off or compartmentalize the reservoir? And then smearing of fine-grained shales or mudstones and things like that along faults is another very important thing that is difficult to predict. It requires continuation laterally and vertically, which is sometimes the case, but not always. So we looked at this experiment before, where we have clay layers 1, 2, 3, 4 in sand, and we can see how this works with the clay layers being smeared out along the fault, forming an impassable membrane that would hinder the fluids to cross the fault. Juxtaposition is really important when we're considering flow across faults, whether the reservoir is in touch with itself or not. For example, here we have this fault we looked at before. It has 2 shear surfaces here, slip surfaces, and because we have 2, we have communication in terms of lithologic contact across the fault, and fluids probably can flow from one side to the other like this, unless there's a very strong fault rock development here. Now in the case shown to the right, which is a photoshopped version of the first picture, where if we only have one fault, or if we think we have only one fault because of resolution issues, we would end up saying that this fault is not providing any communication for this reservoir. It's a sealing fault. It seals off this layer from the left-hand side, between the left and right-hand side. So no communication, no flow of fluids across this fault. And that's a good example. We see faults on seismic lines. We, again, just draw a single line, but remember that these lines can be very different in detail. It could be a single fault, but it could also be a fault zone, and also fault drag is sometimes something to be considered when we think about communication across faults. And these are very different things, very difficult things to predict. And faults and fault damage zones can be very different in terms of communication and fluid flow. Here we have a fault in a sandstone siliciclastic unit, and there's a lot of deformation bands in the hanging wall and footwall that reduce permeability and porosity toward the fault core. In this case here, which is an illustration of basement fault deformation, we see green and blue fractures increasing in frequency close to the fault, and these fractures conduct fluids, so we will have an increase in the overall porosity and permeability the closer we get to the fault, the higher the permeability. And then we're back to these two maps, and the point to be made here is connectivity. The low strain version, or the low strain example to the left, shows faults that are not very well connected, so low connectivity, so the faults will not influence fluid flow in the same way as in the right-hand case, where faults are much more connected and the reservoir will be much more compartmentalized, split up into different domains, each of which requires at least one well penetration to produce hydrocarbons or inject fluids. And we also mentioned fault linkage and ramps earlier on, and these are very important structures that influence the fluid flow in a reservoir, especially during production. They are pathways for fluids to cross faults, ways that fluids can cross from one side of the fault to the other. And then it's useful to remember that faults interact in both the horizontal and vertical direction. So we have these overlap structures in 3 dimensions, as shown in this figure to the right. Here's an example of a fault that is segmented. This is from the Arches National Park in Utah, and the red sandstones in the back and center are separated from the more greenish rocks in the front by this fault zone. And as you can see from this interpretation, this fault is built up of individual segments that are only partly linked up. And in there are ramps, this one for example, that can be a pathway for fluids, sort of a bridge for fluids to cross from one side of the fault zone to the other. So that takes us to the last slide that summarizes some of the complexities that we oftentimes encounter in fault population, normal faults in this case, with fault zones, all kinds of relay structures and fault linkage structures that are very important for communication. We have fault lenses, we have fault smearing of fine-grained layers, and fault rock development, and many other structures. So we need to understand these and be able to predict them to some extent to be able to deal with fluid flow in a reservoir. So in this presentation we basically just scratched the surface of a very big field. But maybe I have been able to give the impression that faults are complex structures with features and characteristics that usually vary quite rapidly along strike and dip. We pointed at important components such as the fault core, fault zone, fault damage zone, fault drag. And these elements show different effects on fluid flow depending on lithology, burial depth, connectivity, geometry, and so on. And understanding faults with all their variability is really, really challenging, but not impossible. And I think faults and fault structures deserve more attention in the future. So thank you for listening to this presentation.